Hello there and welcome to Sleep Science Chronicles. Tonight we turn our gaze upward, far beyond the familiar glow of our own sun, into the vast and ancient darkness where countless other suns are born, live out their long lives, and eventually fade or explode into the cosmos. This is a journey through the life and death of stars. Stars are not eternal. They are born from clouds of gas and dust. They burn for millions or billions of years, and they die in ways both gentle and catastrophic. Some collapse into themselves and vanish from sight. Others explode with such violence that they outshine entire galaxies for a brief, brilliant moment, and in their deaths, they scatter the very elements that make planets, oceans, and living things possible. Tonight we will trace this cosmic story from beginning to end. We will visit stellar nurseries where new suns are taking their first breath. We will witness the steady burning of stars in their prime, and we will follow them into their final chapters, where gravity and time conspire to create some of the strangest objects in the universe. Some of what we discover will be peaceful, like the slow cooling of a white dwarf over trillions of years. Other moments will be violent beyond imagination, like the core collapse of a massive star in a fraction of a second. But through it all, there is a quiet beauty, a rhythm of creation and destruction that has been unfolding since the universe was young. You do not need to remember every detail. You do not need to stay awake for the entire journey. Let the words drift past you like starlight traveling across the void. If sleep finds you somewhere along the way, that is perfectly fine. The stars will still be there, burning in the darkness, whether we are watching or not. And before we begin, if these calm and curious explorations help you unwind or give you a quiet place to rest your thoughts, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. But for now, let yourself settle in, let your breath slow, and let us begin. The story of any star begins not with fire, but with cold. In the vast spaces between existing stars, there are enormous clouds of gas and dust called nebulae. These clouds are mostly hydrogen, the simplest and most abundant element in the universe, mixed with traces of helium and tiny grains of heavier elements left behind by earlier generations of stars. The clouds are impossibly thin by earthly standards. If you could scoop up a cubic meter of nebular gas, you would find only a few hundred atoms floating in that space. And yet, these clouds can stretch for dozens of light years, containing enough material to form thousands of suns. For most of their existence, these clouds simply drift through the galaxy, too diffuse to collapse under their own gravity. But sometimes, something disturbs them. A nearby supernova sends a shock wave rippling through the cloud. Two galaxies pass close to each other, and their gravitational pull stirs the gas. Or the cloud simply drifts into a denser region of the galaxy, where compression is more likely. When this happens, parts of the cloud begin to clump together. Gravity, patient and persistent, starts to gather the scattered atoms into denser pockets. Once a region of the cloud becomes dense enough, a process begins that cannot easily be reversed. Gravity pulls material inward, and as the gas falls toward the center, it heats up. The more material that gathers, the stronger the gravitational pull becomes, and the faster the collapse proceeds. What was once a cold, dark pocket of gas begins to glow with infrared light, the heat of compression radiating outward into space. This collapsing clump is called a protostar. It is not yet a true star because nuclear fusion has not begun in its core. but it is growing steadily, drawing in more and more material from the surrounding cloud. The protostar is often surrounded by a swirling disk of gas and dust, and from this disk, planets may eventually form. Jets of material sometimes shoot out from the poles of the protostar, punching through the surrounding cloud and announcing to the universe that something new is being born. The protostellar phase can last for hundreds of thousands of years. During this time, the core of the protostar grows hotter and denser. The temperature rises from a few thousand degrees to tens of thousands, then to hundreds of thousands. The pressure at the center becomes immense, crushing the hydrogen atoms closer and closer together. And then, when the core temperature reaches about 10 million degrees, something remarkable happens. The hydrogen atoms are moving so fast and are packed so tightly that they begin to fuse together, forming helium and releasing enormous amounts of energy in the process. This is the moment a star is born. Nuclear fusion ignites in the core, and the energy released creates an outward pressure that balances the inward pull of gravity. The star stops collapsing and settles into a state of equilibrium that can last for millions or even billions of years. The long, slow burning of hydrogen has begun. The newborn star continues to clear away the remnants of its birth cloud. Stellar winds, streams of charged particles flowing outward from the star's surface, push the surrounding gas and dust away. Eventually, the star emerges from its cocoon, shining brightly in visible light for the first time. If there are planets forming in the disk around it, they too begin to take shape, coalescing from the leftover material that did not fall into the star itself. Not all protostars succeed in becoming true stars. If a collapsing clump of gas does not gather enough material, the core may never reach the temperature needed for hydrogen fusion. These failed stars are called brown dwarfs. They glow dimly with the heat of their formation and the slow fusion of a rare form of hydrogen called deuterium. But they never achieve the sustained nuclear burning of a true star. Brown dwarfs are strange objects, somewhere between giant planets and small stars, and the galaxy is full of them, drifting unseen through the darkness. The mass of a star at birth determines almost everything about its future. A star with very little mass will burn slowly and dimly, perhaps for trillions of years. A star with enormous mass will burn hot and bright, exhausting its fuel in just a few million years. Our own sun falls somewhere in the middle, a yellow dwarf with enough fuel to shine steadily for about 10 billion years. It is currently about halfway through its life, a middle-aged star by cosmic standards. Stars spend the majority of their lives in a phase called the main sequence. During this phase, they are fusing hydrogen into helium in their cores, and the energy released keeps them stable against gravitational collapse. The main sequence is not a place or a path through space. It is a description of a star's internal state, a long era of steady burning that defines the prime of stellar life. Our sun has been on the main sequence for about 4.6 billion years and will remain there for another 5 billion or so. The color of a main sequence star reveals its temperature. The hottest stars burn blue or blue-white, with surface temperatures exceeding 20,000 degrees. Cooler stars glow yellow or orange, with temperatures between 3,000 and 6,000 degrees. The coolest main sequence stars are red, barely hot enough to sustain hydrogen fusion, glowing with a dim and gentle light. These red dwarfs are by far the most common type of star in the galaxy, outnumbering all other types combined. Red dwarfs are miserly with their fuel. They burn so slowly that they can shine for tens of billions of years, perhaps even hundreds of billions. The universe is only about 13.8 billion years old, which means that no red dwarf has ever died of old age. Every red dwarf that has ever formed is still burning today, patiently fusing hydrogen in its core, waiting out the long eons. In the far future, when most other stars have faded, the red dwarfs will still be there, the last sources of starlight in an aging universe. At the other end of the scale are the blue giants and supergiants, stars with masses 10, 20, or even 100 times that of our sun. These stars burn through their fuel at a ferocious rate. A blue supergiant might exhaust its hydrogen supply in just a few million years, a blink of an eye compared to the lifespan of a red dwarf. The brightest of these stars can be seen across vast distances, beacons of light that outshine entire galaxies. But their brilliance comes at a cost. They live fast and die young, often in spectacular explosions that seed the universe with heavy elements. The structure of a main sequence star is elegantly simple. At the center is the core, where nuclear fusion takes place. Surrounding the core is a thick layer called the radiative zone, where energy slowly diffuses outward through countless absorptions and re-emissions by atoms. Above that is the convective zone, where hot plasma rises toward the surface, cools, and sinks back down in great churning currents. Finally, there is the photosphere, the visible surface of the star where light escapes into space. The core of a star like our sun is extraordinarily hot and dense. The temperature exceeds 15 million degrees, and the pressure is about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, hydrogen nuclei are stripped of their electrons and move so fast that they can overcome their natural repulsion and fuse together. Each fusion reaction converts a tiny amount of mass into energy, according to Einstein's famous equation. The sun converts about 4 million tons of mass into energy every second, and it has been doing so for billions of years. The energy produced in the core does not escape immediately. A photon of light created by fusion in the sun's core may take tens of thousands or even hundreds of thousands of years to reach the surface. It bounces from atom to atom, absorbed and re-emitted countless times, slowly working its way outward through the dense plasma. By the time it reaches the surface, it has lost much of its original energy, shifting from high-energy gamma rays to the visible light we see. This journey from core to surface is called the random walk, and it is one of the slowest migrations in nature. Once light reaches the photosphere, it escapes into space and travels at 300,000 kilometers per second. The light we see from the sun today was generated in the core long before human civilization began. We are always looking at ancient energy, the delayed glow of reactions that happened when our ancestors were still learning to walk upright. In a sense, sunlight is a message from the past, arriving at last after a long journey through the star's interior. The surface of the sun is not smooth. It is covered with granules, each one a convection cell where hot plasma rises, spreads out, cools, and sinks back down. Each granule is about 1,000 kilometers across and lasts for only 10 or 15 minutes before being replaced by a new one. Seen from above, the surface looks like a pot of boiling soup, constantly churning and shifting. Occasionally, darker regions called sunspots appear where magnetic fields are so strong that they inhibit convection and lower the local temperature. Sunspots come and go in cycles lasting about 11 years. At the peak of the cycle, the sun's surface may be dotted with dozens of spots, some larger than the Earth. At the cycle's minimum, the surface may be almost entirely clear. The magnetic activity associated with sunspots can produce solar flares, sudden releases of energy, then send bursts of radiation and charged particles out into space. When these particles reach Earth, they can disrupt satellites, power grids, and radio communications, and they create the shimmering auroras near the poles. Above the photosphere lies the chromosphere, a thin layer of gas that is usually invisible against the bright surface below. During a total solar eclipse, when the moon blocks the photosphere, the chromosphere becomes visible as a thin pink or reddish ring around the darkened sun. Above the chromosphere is the corona, an even fainter halo of extremely hot gas that extends millions of kilometers into space. The corona is much hotter than the photosphere, reaching temperatures of 1 to 3 million degrees, a puzzle that scientists are still working to fully understand. The solar wind flows outward from the corona, a constant stream of charged particles that fills the solar system. This wind pushes against the atmospheres of planets, strips away unprotected gases, and carves out a vast bubble in the interstellar medium called the heliosphere. The heliosphere extends far beyond the orbit of Pluto, marking the region of space dominated by our sun's influence. At the edge of the heliosphere, the solar wind meets the thin gas between the stars, creating a boundary zone that spacecraft are only now beginning to explore. Stars like our sun will remain on the main sequence for billions of years, but eventually, the hydrogen in the core begins to run out. Fusion continues in a shell surrounding the core, but the core itself, now mostly helium, begins to contract under its own gravity. As the core shrinks, it heats up, and this extra heat causes the outer layers of the star to expand. The star grows larger and cooler at the surface, shifting from yellow to orange to red. It has become a red giant. The transformation from main sequence star to red giant is slow by human standards, but rapid by cosmic ones. Our sun will begin this transition in about 5 billion years. When it does, it will swell to perhaps 100 times its current diameter, engulfing the orbits of Mercury and Venus, and possibly reaching Earth. The oceans will boil away. The atmosphere will be stripped into space. The planet that has been our home for all of human history will be scorched and sterilized, perhaps swallowed entirely by the expanding sun. Inside the red giant, the helium core continues to contract and heat. When the temperature reaches about 100 million degrees, a new kind of fusion becomes possible. Helium nuclei begin to fuse together, forming carbon and oxygen. This process, called the triple alpha process, releases energy and stabilizes the core for a time. The star settles into a new phase of life, burning helium in its core and hydrogen in a shell around it. This helium-burning phase is shorter than the main sequence, lasting perhaps 100 million years for a sun-like star. For stars like our sun, this is nearly the end of the road. When the helium in the core is exhausted, there is not enough mass to compress the carbon-oxygen core to the temperatures needed for further fusion. The core contracts until it is supported by a quantum mechanical effect called electron degeneracy pressure. The outer layers of the star, no longer held in place by radiation from the core, drift away into space, forming a glowing shell of gas called a planetary nebula. At the center, the exposed core remains as a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. Planetary nebulae are among the most beautiful objects in the sky. They glow in vivid colors, illuminated by the ultraviolet radiation from the hot white dwarf at their center. Some are spherical. Others are shaped like hourglasses, butterflies, or rings. The shapes depend on the star's rotation, magnetic fields, and interactions with companion stars or planets. Each planetary nebula is unique, a fingerprint left behind by a dying star. They last for only a few tens of thousands of years before fading and dispersing into the interstellar medium, their material eventually recycled into new generations of stars. White dwarfs are strange and fascinating objects. A typical white dwarf contains about half the mass of the Sun, but is compressed into a volume roughly the size of Earth. The density is staggering. A teaspoon of white dwarf material would weigh several tons. The surface gravity is tens of thousands of times stronger than Earth's. If you could stand on a white dwarf, you would be crushed instantly, your body compressed to a thin film on the surface. White dwarfs no longer generate energy through nuclear fusion. They shine only because they are hot, radiating away the heat accumulated during their long lives. Over billions and trillions of years, they slowly cool and fade, transitioning from white to yellow to red to a dim, cold remnant called a black dwarf. The universe is not old enough for any black dwarfs to exist yet. The coolest white dwarfs we have observed are still relatively warm, glowing faintly in the darkness. In the far future, black dwarfs will be among the last remaining objects in a universe that has grown cold and dark. Massive stars follow a different path. When a star with more than about 8 times the mass of the Sun exhausts the hydrogen in its core, it too becomes a red giant, or more accurately, a red supergiant. But unlike smaller stars, these giants have enough mass to continue fusing heavier and heavier elements. After helium comes carbon, then neon, then oxygen, then silicon. Each new fusion stage lasts for a shorter time than the one before. Carbon burning might last for 1,000 years. Silicon burning lasts for only a few days. The structure of a massive star in its final stages resembles an onion. At the center is an iron core, surrounded by shells of silicon, oxygen, neon, carbon, helium, and hydrogen, each shell fusing a different element. Iron is the end of the line for fusion. Fusing iron does not release energy. It requires energy. When the core becomes mostly iron, there is no longer any source of outward pressure to support the star against gravity. The core collapses catastrophically, and the star dies in one of the most violent events in the universe. This is a core collapse supernova. In less than a second, the iron core collapses from a sphere roughly the size of Earth to a ball just 20 kilometers across. The outer layers of the star, no longer supported, come crashing down onto the core. They bounce off the incompressible core and are blown outward in a shock wave that tears the star apart. For a few weeks, the supernova shines brighter than billions of suns, visible across the universe. Then it fades, leaving behind either a neutron star or a black hole. The energy released in a supernova is almost beyond comprehension. In a fraction of a second, the collapsing core releases more energy than our Sun will produce in its entire 10 billion year lifetime. Most of this energy is carried away by neutrinos, ghostly particles that barely interact with matter. A supernova produces so many neutrinos that despite their weak interactions, A few can be detected by instruments on Earth when a supernova occurs in our galaxy. The last time this happened was in 1987 when a star exploded in a nearby galaxy called the Large Magellanic Cloud. Neutrino detectors around the world registered a brief pulse of particles, the first direct observation of neutrinos from a supernova. The shock wave from a supernova does more than destroy the star. As it passes through the outer layers, it compresses and heats the gas to such extreme conditions that new elements are forged. Elements heavier than iron, including gold, silver, platinum, and uranium, are created in the intense environment of the explosion. These heavy elements are scattered into space, along with the rest of the star's material, enriching the interstellar medium with the building blocks of planets and life. Every atom of gold in every wedding ring on Earth was forged in the heart of an exploding star. The remnants of supernovae spread out into space over thousands of years, forming expanding shells and filaments of hot gas. These supernova remnants are visible across the electromagnetic spectrum, glowing in radio waves, X-rays, and visible light. The Crab Nebula, one of the most famous supernova remnants, is the result of an explosion observed by Chinese astronomers in the year 1054. The expanding cloud of gas is still visible today, powered by a rapidly spinning neutron star at its center. Neutron stars are the collapsed cores of massive stars that were not quite massive enough to form black holes. They are incredibly dense, packing 1 to 2 times the mass of the Sun into a sphere only about 20 kilometers across. The density is so extreme that atomic nuclei are crushed together, and the star is composed almost entirely of neutrons. A teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is about 200 billion times stronger than Earth's gravity. Neutron stars spin rapidly, often completing hundreds of rotations per second. They have intense magnetic fields, trillions of times stronger than Earth's. As they spin, beams of radiation sweep out from their magnetic poles, like the beam of a lighthouse. If one of these beams happens to point toward Earth, we see a regular pulse of radio waves or X-rays. These pulsing neutron stars are called pulsars, and they are among the most precise natural clocks in the universe. Some pulsars keep time so accurately that they rival the best atomic clocks on Earth. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student in Cambridge. The regular pulses were so precise that for a brief time, astronomers wondered if they might be signals from an alien civilization. The source was jokingly designated LGM1 for Little Green Men. But further observations revealed natural explanations, and pulsars are now understood as rapidly spinning neutron stars. Thousands of pulsars have been discovered since then, scattered throughout the galaxy. Some neutron stars are even more extreme. Magnetars are neutron stars with magnetic fields hundreds of times stronger than ordinary pulsars. These magnetic fields are so intense that they can distort the shapes of atoms and even affect the fabric of space itself. Magnetars occasionally release enormous bursts of energy, flares so powerful that they can be detected from across the galaxy. A magnetar flare in 2004 was so bright that it temporarily ionized part of Earth's upper atmosphere, even though the magnetar was 50,000 light-years away. When the core of a collapsing star is too massive to become a neutron star, it continues to collapse until nothing can stop it. The core shrinks past the point of no return, forming a black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole, beyond which escape is impossible, is called the event horizon. Once something crosses the event horizon, it is lost to the outside universe forever. Black holes come in different sizes. Stellar black holes, formed from the collapse of massive stars, typically contain 5 to 30 times the mass of the Sun. Supermassive black holes, found at the centers of galaxies, contain millions or even billions of solar masses. How supermassive black holes formed is still an active area of research. They may have grown from smaller black holes that merged over cosmic time, or they may have formed directly from the collapse of massive gas clouds in the early universe. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners. They do not suck in everything around them any more than any other object of the same mass would. If our Sun were replaced by a black hole of the same mass, the planets would continue to orbit as before, undisturbed. The danger of a black hole comes only when you get close, when the immense gravity can stretch and compress matter in a process colorfully called spaghettification. Anything falling into a stellar black hole would be torn apart by tidal forces long before reaching the event horizon. The environment around a black hole can be extremely violent. Matter falling toward a black hole forms a swirling disk called an accretion disk. Friction within the disk heats the gas to millions of degrees, causing it to glow brightly in X-rays. Some of the most luminous objects in the universe are powered by black holes actively consuming matter. Quasars, found in the centers of distant galaxies, are supermassive black holes surrounded by accretion disks so bright that they outshine their entire host galaxies. Black holes can also launch jets of material at nearly the speed of light. These jets extend for thousands or even millions of light years, far beyond the boundaries of their host galaxies. The mechanism that produces jets is not fully understood, but it involves the interaction of the black hole's spin, its magnetic field, and the infalling matter. These jets carry enormous amounts of energy and can influence the evolution of galaxies across cosmic distances. The interior of a black hole is a mystery. At the center, according to general relativity, is a singularity, a point of infinite density where the known laws of physics break down. What happens at the singularity is unknown. It may be that a complete theory of quantum gravity, which unifies general relativity with quantum mechanics, is needed to understand what occurs there. Until such a theory is developed, the singularity remains a placeholder for our ignorance, a reminder that there are still deep questions about the nature of space, time, and gravity that we can't yet answer. In 2019, astronomers released the first direct image of a black hole. The image showed the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The black hole itself is invisible, but the bright ring of hot gas surrounding it clearly shows the shadow of the event horizon. The image was created by linking radio telescopes around the world into a virtual telescope the size of Earth, an achievement that took years of planning and computation. It was a historic moment, the first time humanity had seen direct visual evidence of an event horizon. Gravitational waves offer another way to study black holes. When two black holes spiral together and merge, they create ripples in the fabric of space-time that propagate outward at the speed of light. These gravitational waves were first detected in 2015 by the LIGO observatories, confirming a prediction made by Einstein a century earlier. Since then, dozens of black hole mergers have been detected, revealing a population of black holes with masses larger than expected from standard stellar evolution. The study of gravitational waves has opened an entirely new way of observing the universe. The merger of two black holes is one of the most energetic events in the universe. In the final moments before merger, the two black holes are orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light. The gravitational waves they emit carry away enormous amounts of energy. In the first detected merger, the equivalent of about 3 solar masses was converted into gravitational wave energy in a fraction of a second. For a brief moment, that single merger released more power than all the stars in the observable universe combined. Neutron star mergers are even more revealing. When two neutron stars spiral together and collide, they produce gravitational waves, a burst of gamma rays, and a kilonova, a glowing cloud of heavy elements forged in the collision. In 2017, astronomers observed a neutron star merger for the first time across multiple wavelengths, from gravitational waves to gamma rays to visible light to radio waves. The observations confirmed that neutron star mergers are a major source of heavy elements like gold and platinum, solving a long-standing mystery about where these elements come from. The cycle of stellar birth and death has been repeating for billions of years. The first stars formed a few 100 million years after the Big Bang, coalescing from clouds of hydrogen and helium that had no heavier elements at all. These first stars were probably massive and short-lived, burning through their fuel quickly and exploding as supernovae. Their explosions enriched the surrounding gas with the first heavy elements, carbon and oxygen and iron, setting the stage for the next generation of stars. Each generation of stars builds on the legacy of the ones that came before. The gas clouds that form new stars contain trace amounts of heavy elements produced by earlier supernova. Some of these elements become part of the new stars. Others become part of the dust grains and planetesimals that form planets. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these were forged in the cores of stars that lived and died before our sun was born. You are, quite literally, made of stardust. The stars we see in the night sky are not distributed evenly. They cluster together in galaxies, vast islands of hundreds of billions of stars bound together by gravity. Our own galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars, each one at a different stage of its life. Some are newborns, still wrapped in the gas clouds from which they formed. Others are ancient, older than the Earth itself, slowly cooling as they drift through the galactic haze. The Milky Way is a barred spiral galaxy, with a central bulge of older stars surrounded by sweeping spiral arms where star formation is most active. Our sun lies in one of these arms, about 26,000 light-years from the galactic center. From our perspective, the galaxy appears as a faint band of light stretching across the night sky, the combined glow of billions of distant stars too far away to see individually. On a clear, dark night, far from city lights, you can trace the path of the galaxy from horizon to horizon, a river of light that our ancestors watched and wondered about for thousands of generations. The spiral arms of the Milky Way are not solid structures. They are density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center. Stars pass through the arms, spending some time in the denser region before moving on. The arms appear bright because the compression triggers star formation, and the young, massive stars that form there are extremely luminous. Older, dimmer stars are distributed more evenly throughout the galaxy, but they do not stand out against the glare of their younger siblings. Star formation in the Milky Way is not constant. It has varied over the history of the galaxy, with periods of intense activity followed by quieter intervals. Currently, the Milky Way forms new stars at a rate of about 1 to 3 solar masses per year. This may sound modest, but it adds up over billions of years. The galaxy has been forming stars for most of its 13 billion year history, and the results are scattered across the sky in clusters, associations, and the diffuse stellar population of the disk and halo. Some stars form in isolation, collapsing from small dense cores within molecular clouds, but most stars form in groups, born from the same cloud at roughly the same time. These stellar nurseries produce open clusters, loose groupings of a few hundred to a few thousand stars that share a common origin. The Pleiades, visible to the naked eye as a small dipper-shaped pattern in the constellation Taurus, is one of the most famous open clusters. Its stars are young, only about 100 million years old, and they are still surrounded by wisps of the nebula from which they formed. Open clusters do not last forever. Over hundreds of millions of years, gravitational interactions with other stars and with the galactic disk gradually pull the cluster apart. The stars drift away from each other, spreading out along their orbits until the cluster is no longer recognizable. The Sun may have been born in such a cluster, but if so, its siblings have long since scattered across the galaxy. Somewhere out there, stars that formed from the same cloud as our Sun are shining in distant parts of the Milky Way, unaware of their shared origin. Globular clusters are very different from open clusters. They are ancient, dense, and massive, containing hundreds of thousands or even millions of stars packed into a roughly spherical shape. The stars in globular clusters are among the oldest in the galaxy, formed more than 10 billion years ago when the Milky Way was young. They orbit the galactic center in elongated paths, spending most of their time in the sparse halo far above and below the galactic disk. The cores of globular clusters are extraordinarily crowded. Stars are packed so closely together that collisions and close encounters are relatively common. These interactions can produce exotic objects like blue stragglers, stars that appear younger and bluer than they should be given the age of the cluster. Blue stragglers are thought to form when two stars merge, combining their mass and resetting the clock on stellar evolution. In the dense hearts of globular clusters, such mergers happen often enough to populate the cluster with these rejuvenated stars. Globular clusters may also harbor intermediate mass black holes, objects with masses between stellar black holes and the supermassive black holes at the centers of galaxies. These intermediate mass black holes are difficult to detect, but their gravitational influence on surrounding stars can reveal their presence. If they exist, they may have formed from the mergers of many smaller black holes in the dense cluster environment, or they may be remnants of the first generation of massive stars that formed in the early universe. The distances between stars are vast, beyond ordinary comprehension. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away. This means that the light we see from Proxima Centauri tonight left that star 4 years ago. If Proxima Centauri were to suddenly vanish, we would not know for 4 years. The universe is so large that we are always looking into the past, seeing things not as they are, but as they were when their light began its journey toward us. If the sun were the size of a grain of sand, Proxima Centauri would be another grain of sand about 4 miles away. The space between them would be essentially empty, with only the occasional atom of interstellar gas drifting through the void. This is the true nature of the galaxy: vast stretches of nearly perfect vacuum punctuated by tiny points of light separated by unimaginable distances. The night sky looks crowded only because we cannot perceive the depth, the billions of miles that separate each star from its neighbors. Despite these distances, stars are not completely isolated. They are embedded in a thin soup of gas and dust called the interstellar medium. This material fills the space between stars, though it is so sparse that it would count as a laboratory vacuum by earthly standards. The interstellar medium is not uniform. It contains denser clouds where new stars can form, hot bubbles carved out by stellar winds and supernovae, and long filaments shaped by magnetic fields and galactic rotation. The interstellar medium is enriched with heavy elements from generations of stellar death. When a star explodes as a supernova, its outer layers are scattered into space, mixing with the surrounding gas. Over billions of years, this process has gradually increased the abundance of heavy elements in the galaxy. The oldest stars, formed when the galaxy was young, contain very few heavy elements. Younger stars, like our Sun, contain a richer mix of elements inherited from the many supernovae that came before. Astronomers measure the heavy element content of a star using a quantity called metallicity. In astronomical terminology, any element heavier than helium is considered a metal, even elements like carbon and oxygen that chemists would not classify that way. A star with high metallicity formed from gas that had been enriched by many previous generations of stars. A star with low metallicity formed from more pristine gas, closer to the original composition of the universe. The most metal-poor stars known are ancient relics from the early universe. They contain only trace amounts of elements heavier than hydrogen and helium, sometimes less than 1/1,000,000th the abundance found in the Sun. These stars are rare and difficult to find, but they provide valuable clues about the conditions in the early universe and the nature of the first stars. Some of the most metal-poor stars may have formed from gas that was enriched by a single supernova, allowing astronomers to study the nucleosynthesis of individual ancient explosions. The first stars in the universe, sometimes called population 3 stars, have never been directly observed. They are thought to have formed a few 100 million years after the Big Bang, from clouds of hydrogen and helium that contained no heavy elements at all. Without heavy elements to help the gas cool and collapse, these first stars may have been extremely massive, perhaps hundreds of times the mass of the Sun. They would have burned hot and bright, living for only a few million years before exploding and seeding the universe with the first heavy elements. The explosions of population 3 stars may have been unlike any supernovae we see today. Some theoretical models suggest that the most massive of these stars could have produced pair instability supernova, explosions so powerful that they completely destroy the star, leaving no remnant behind. In a pair instability supernova, the core of the star becomes so hot that photons begin to convert into pairs of electrons and positrons. This removes pressure support from the core, triggering a runaway collapse and explosion that releases more energy than any other type of stellar death. The transition from the first generation of stars to the second generation marked a fundamental change in the universe. Once heavy elements were present in the interstellar medium, gas clouds could cool more efficiently, allowing smaller, longer-lived stars to form. The second generation included stars similar to those we see today, with a range of masses and lifespans. Some of these second-generation stars are still shining, ancient beacons that have witnessed most of the history of the universe. Binary stars are far more common than solitary stars like our Sun. More than half of all stars in the galaxy are part of binary or multiple star systems, two or more stars orbiting a common center of mass. Some binaries are so close that they almost touch, their surfaces separated by only a thin gap. Others are so distant that their orbital periods are measured in thousands of years. The diversity of binary configurations leads to a rich variety of phenomena, from eclipsing binaries that dim regularly as one star passes in front of the other, to interacting binaries where mass flows from one star to the other. Close binary stars can exchange mass in dramatic ways. If one star in a binary evolves faster than its companion and expands into a red giant, its outer layers may spill onto the other star. This mass transfer can alter the evolution of both stars, sometimes dramatically. The star receiving mass may gain enough material to become a blue straggler, appearing younger than it actually is. The star losing mass may be stripped down to its core, becoming a white dwarf or neutron star long before it would have if it had evolved in isolation. Some mass-transferring binaries produce cataclysmic variables, systems where a white dwarf pulls material from a companion star. The material forms an accretion disk around the white dwarf and periodically erupts in outbursts called novae. A nova occurs when hydrogen accumulates on the surface of the white dwarf until it reaches a critical temperature and ignites in a runaway fusion reaction. The surface of the white dwarf briefly blazes with light, then fades as the accumulated material is blown away. Unlike supernovae, novae do not destroy the white dwarf. The process can repeat many times over millions of years. Classical novae can increase in brightness by a factor of 10,000 or more in just a few days. Throughout history, novae have appeared as new stars in the sky, visible for weeks or months before fading from view. The word nova comes from the Latin for new, reflecting the ancient belief that these events represented the birth of new stars. We now know that novae are not births, but eruptions, thermonuclear explosions on the surfaces of white dwarfs in binary systems. If enough mass accumulates on a white dwarf through binary mass transfer, the white dwarf can reach a critical limit called the Chandrasekhar mass, about 1.4 times the mass of the Sun. At this point, the white dwarf can no longer support itself against gravitational collapse. The result is a Type 1, a supernova, a thermonuclear explosion that completely destroys the white dwarf. Type 1a supernovae are remarkably consistent in their brightness, making them valuable tools for measuring cosmic distances. By comparing the observed brightness of a Type 1a supernova with its known intrinsic luminosity, astronomers can calculate how far away it is. Type 1a supernovae played a crucial role in one of the most surprising discoveries in modern cosmology. In the late 1990s, astronomers used Type 1a supernovae to measure the distances to faraway galaxies and found that the universe is not just expanding, but accelerating. Something is pushing the galaxies apart faster and faster over time. This mysterious force, called dark energy, makes up about 68% of the total energy content of the universe. Its nature remains one of the deepest unsolved problems in physics. The life cycles of stars are intimately connected to the evolution of galaxies. When galaxies collide and merge, the resulting gravitational disturbances can trigger intense bursts of star formation. Gas clouds that might have remained stable for billions of years are compressed and pushed over the threshold for collapse. Millions of new stars can form in a relatively short period, transforming the merged galaxy. Some of these starbursts are so intense that they can be seen across the universe, the combined light of countless young stars outshining everything else. The Milky Way is not immune to such encounters. In about 4 to 5 billion years, our galaxy will collide with the Andromeda Galaxy, our nearest large neighbor. The collision will unfold over hundreds of millions of years, with the two galaxies passing through each other, separating and falling back together repeatedly before finally merging into a single, larger galaxy. The night sky will be transformed, the familiar constellations disrupted as stars are flung onto new orbits. But individual stellar collisions will be rare. The stars are so far apart that even when galaxies collide, most stars pass by each other without incident. The collision between the Milky Way and Andromeda will trigger a new wave of star formation. Gas clouds in both galaxies will be compressed and destabilized, leading to the birth of millions of new stars. Some of these will be massive stars that will live fast, die young, and explode as supernovae, enriching the merged galaxy with fresh, heavy elements. Others will be modest stars like our Sun, settling into long, quiet lives on the main sequence. The cycle of stellar birth and death will continue, as it has for billions of years. Stars influence their environments in ways that extend far beyond their immediate surroundings. The radiation from hot, massive stars can ionize the gas in nearby nebulae, creating glowing clouds called H2 regions. The stellar winds from these same stars carve bubbles and channels in the interstellar medium. When the stars die as supernovae, they inject energy and momentum into the surrounding gas, driving turbulence that can propagate for thousands of light years. The cumulative effect of many supernovae can blow superbubbles, enormous cavities hundreds of light years across, cleared of gas by the combined force of multiple explosions. Stellar feedback, as this influence is called, plays a crucial role in regulating star formation. Without feedback, gas would collapse and form stars too efficiently, using up the available material in a relatively short time. The energy injected by massive stars heats the gas and prevents it from collapsing too quickly. This self-regulation helps explain why galaxies form stars at a relatively steady rate over billions of years, rather than in a single intense burst. The balance between gravity pulling gas together and stellar feedback pushing it apart determines the pace of cosmic evolution. The deaths of massive stars also seed the universe with cosmic rays, high-energy particles that travel at nearly the speed of light. Cosmic rays are mostly protons and atomic nuclei, accelerated to enormous energies by the shock waves of supernovae. These particles fill the galaxy, bouncing off magnetic fields and wandering through the interstellar medium for millions of years before escaping into intergalactic space or colliding with atoms and producing showers of secondary particles. cosmic rays constantly bombard the Earth, though our atmosphere and magnetic field protect us from most of their effects. Some cosmic rays have energies far beyond anything we can produce in particle accelerators on Earth. The most energetic cosmic rays detected have energies equivalent to a baseball thrown at 60 miles per hour, concentrated in a single subatomic particle. The origins of these ultra-high energy cosmic rays are still uncertain. They may come from the most extreme environments in the universe, the jets of supermassive black holes, the collisions of galaxy clusters, or exotic phenomena we have not yet identified. Each detection of an ultra-high energy cosmic ray is a message from one of these distant, violent places. The elements forged in stars and scattered by supernovae eventually find their way into new stars, planets, and living things. The process is slow, unfolding over billions of years, but it is inexorable. Every atom heavier than hydrogen has been processed through at least one star, and many have been through several. The carbon in your body may have been part of a red giant billions of years ago, ejected in a stellar wind and drifting through space for eons before being incorporated into the cloud that formed our solar system. The oxygen you breathe was forged in the cores of massive stars, released in supernovae that scattered it across the galaxy. The calcium in your bones was created in the same explosions, along with the silicon that makes up most of the Earth's crust. The iron in your blood was synthesized in the final moments of a dying star, compressed and heated to temperatures beyond imagination before being blasted into space. You are a temporary arrangement of atoms that were once scattered across light years, brought together by gravity and chemistry to form a living being capable of wondering about its own origins. This perspective can be humbling or inspiring, depending on how you look at it. We are small, brief, and fragile, living on a tiny planet orbiting an ordinary star in the outskirts of an average galaxy. But we are also connected to the cosmos in the most intimate way possible. The atoms in our bodies have journeyed through billions of years and countless light years to be here, assembled into beings that can look up at the night sky and recognize their kin in the stars. The sun will not shine forever. In about 5 billion years, it will exhaust the hydrogen in its core and begin its transformation into a red giant. The inner planets will be vaporized or engulfed. The Earth, if it survives, will be a scorched, barren world, its oceans boiled away and its atmosphere stripped into space. Eventually, the sun will shed its outer layers and collapse into a white dwarf, a cooling ember that will fade over trillions of years until it becomes a cold, dark cinder. But 5 billion years is an almost incomprehensible span of time. It is longer than the entire history of life on Earth, longer than the age of the solar system, longer than the time since the first stars formed in the universe. Civilizations may rise and fall thousands of times before the sun begins to die. Humanity, if it survives, may spread to other stars, finding new homes around younger suns. Or we may be long gone, replaced by other forms of intelligence that we cannot imagine. The future is as vast and unknown as the universe itself. The stars we see tonight are snapshots of different moments in stellar evolution. Some are young, still burning bright with the energy of hydrogen fusion. Others are old, swelling into red giants or cooling as white dwarfs. A few are dying even as we watch, their cores collapsing or their surfaces erupting in nova explosions. The night sky is a gallery of stellar life, each point of light a different chapter in the endless story of cosmic birth and death. Variable stars change in brightness over time, sometimes predictably, sometimes erratically. Cavoid variables pulsate regularly, expanding and contracting in cycles that last from days to weeks. The period of a Cepheide's pulsation is directly related to its intrinsic luminosity, a relationship that makes Cepheids invaluable for measuring cosmic distances. By observing the period of a Cepheid in a distant galaxy, astronomers can determine its true brightness and calculate how far away it must be to appear as dim as it does. Mira variables are red giants that pulsate over periods of months to years, changing in brightness by factors of hundreds or even thousands. These stars are near the end of their lives, their outer layers expanding and contracting as they lose mass to stellar winds. Some Miras are so cool that they form molecules and dust grains in their outer atmospheres, shrouding themselves in cocoons of material that they gradually expel into space. The mass lost by Mira variables and other evolved stars enriches the interstellar medium with the products of stellar nucleosynthesis. RR Lyrae stars are another type of pulsating variable, found primarily in globular clusters and the galactic halo. They are older and less luminous than Cepheids, but they also follow a period luminosity relation that makes them useful distance indicators. RR Lyrae stars are tracers of ancient stellar populations, marking the locations of the oldest stars in the galaxy. Their distribution reveals the structure of the galactic halo, a roughly spherical cloud of old stars and globular clusters that surrounds the disk of the Milky Way. Eclipsing binaries are not intrinsically variable, but appear to change in brightness because one star periodically passes in front of the other, as seen from Earth. The most famous eclipsing binary is Algol, the demon star, which dims noticeably every few days as its fainter companion blocks part of its light. Eclipsing binaries provide valuable information about stellar properties. By analyzing the light curve, the pattern of brightness changes over time. Astronomers can determine the sizes, masses, and even shapes of the component stars. Some variable stars are cataclysmic, erupting suddenly and unpredictably. Dwarf novae are binary systems containing white dwarfs that undergo repeated outbursts as material accumulates in their accretion disks and then drains onto the white dwarf surface. Symbiotic stars are binaries containing a red giant and a white dwarf, with complex interactions that produce irregular variations in brightness. These systems offer windows into the physics of mass transfer, accretion, and thermonuclear burning in environments we cannot reproduce on Earth. The most luminous stars in the universe are not ordinary main sequence stars or even red supergiants. They are a rare class of objects called hypergiants, stars with masses exceeding 50 times that of the Sun and luminosities millions of times greater. Hypergiants are unstable, prone to massive outbursts that can eject large fractions of their mass into space. They live for only a few million years before dying in spectacular supernovae or collapsing directly into black holes. Eta Carinae is one of the most famous hypergiants in our galaxy. It is actually a binary system, two massive stars orbiting each other in a highly eccentric path. In the 1840s, Eta Carinae underwent a massive eruption that briefly made it the second brightest star in the sky. The material ejected during this eruption formed the Homunculus Nebula, a bipolar cloud of gas and dust that surrounds the star system today. Eta Carinae is expected to explode as a supernova sometime in the next few 100,000 years, possibly much sooner. When it does, it will be visible in daylight from Earth. Wolf-Rayet stars are another class of extremely luminous massive stars. They are characterized by strong stellar winds that carry away mass at prodigious rates, stripping the outer layers of the star and exposing the products of nuclear fusion in the core. Wolf-Rayet stars appear blue or bluish-white and are surrounded by expanding shells of material shed by their powerful winds. They are rare, representing a brief phase in the evolution of the most massive stars before they explode as supernovae. The most massive stars known have masses approaching 300 times that of the Sun. These monsters push against theoretical limits for how large a star can be. Above a certain mass, the radiation pressure in a star's core becomes so intense that it blows the outer layers away faster than they can accumulate. Stars much more massive than 300 solar masses would be unable to hold themselves together. The most massive stars we observe are dancing on the edge of this limit, barely stable against their own luminosity. Stellar mass loss shapes the late stages of stellar evolution. Red giants and asymptotic giant branch stars lose mass through slow, dense winds that carry processed material into space. More massive stars lose mass through fast, hot winds driven by radiation pressure. In some cases, stars can lose more than half their mass over the course of their lives, dramatically altering their evolutionary paths. A star that begins its life with 50 solar masses might end it with only 10, having shed the rest into the interstellar medium. The mass lost by evolved stars forms a significant fraction of the material available for new star formation. Planetary nebulae, supernova remnants, and stellar winds all contribute to the enrichment and replenishment of the interstellar medium. Without this recycling, the galaxy would gradually run out of raw material for making new stars. The deaths of old stars enable the births of new ones, a cosmic cycle of renewal that has been turning for billions of years. The interstellar medium is not empty space. It contains gas, dust, and magnetic fields that interact in complex ways. The gas is mostly hydrogen, either in atomic or molecular form, with traces of helium and heavier elements. The dust consists of tiny grains of carbon and silicates, each one only a fraction of a micrometer across. These grains absorb and scatter starlight, causing distant stars to appear dimmer and redder than they would otherwise. In regions of particularly dense dust, entire patches of sky can be blocked from view, appearing as dark lanes against the background of stars. Interstellar dust plays a crucial role in the formation of molecules in space. The surfaces of dust grains act as catalysts, bringing atoms together and allowing them to form complex molecules that would be rare in the gas phase alone. Molecular clouds, the densest regions of the interstellar medium, contain hundreds of different molecules including water, ammonia, formaldehyde, and even amino acids. The chemistry of these clouds is intricate and ongoing, producing ever more complex molecules over millions of years. Some of the molecules formed in interstellar clouds are the building blocks of life. Amino acids, the components of proteins, have been detected in meteorites that formed from the dust of the early solar system. Water, essential for life as we know it, is abundant in molecular clouds and in the icy bodies of the outer solar system. The raw materials for life were present in the cloud that formed our sun and planets, inherited from generations of stellar death and interstellar chemistry. In this sense, life on Earth is a continuation of processes that began in the hearts of ancient stars. The life cycle of stars is not just a story of individual objects. It is a story of the universe itself, of how matter is transformed over cosmic time. The universe began with only hydrogen, helium, and traces of lithium, the products of Big Bang nucleosynthesis. Everything else was made in stars, forged by nuclear fusion and scattered by stellar death. The heavy elements in your body, in the earth beneath your feet, in the planets and moons of the solar system, all of these were made inside stars that lived and died before the sun was born. This process of cosmic enrichment continues today. Every supernova adds new heavy elements to the interstellar medium. Every planetary nebula releases carbon, nitrogen, and oxygen into space. Every neutron star merger sprays gold, platinum, and uranium across the galaxy. The universe is slowly getting richer in heavy elements, and the stars of the future will be made of slightly different stuff than the stars of the past. In billions of years, the composition of the galaxy will be measurably different, the cumulative result of countless stellar lives. The night sky is a tapestry woven from the threads of stellar evolution. The stars we see are connected to us by bonds of matter and energy that stretch across billions of years. We are made of star stuff, as the astronomer Carl Sagan famously said, and we are gazing back at the forges that made us. Every point of light is a sun, and many of those suns have planets, and some of those planets may harbor life, looking up at their own night skies and wondering about the stars. The universe contains far more stars than any human mind can truly comprehend. Current estimates suggest there are roughly 200 billion trillion stars in the observable universe. That number is so large that it exceeds the number of grains of sand on all the beaches of Earth. Each one of those stars is a sun, a sphere of plasma undergoing nuclear fusion, shining light into the darkness. Some are smaller and cooler than our sun. Others are vastly larger and more luminous. Together, they form the luminous scaffolding of the cosmos, the bright points that trace the structure of galaxies and galaxy clusters across billions of light years. The observable universe is only the portion of the universe from which light has had time to reach us since the Big Bang. Beyond the edge of the observable universe, there are almost certainly more stars, more galaxies, more of everything, stretching on for distances we may never be able to measure. The true size of the universe is unknown. It may be infinite, extending forever in all directions, or it may be finite but unbounded, curving back on itself in ways that are difficult to visualize. Either way, the number of stars in existence is likely far greater than the number we can see. The light from distant stars carries information about their composition, temperature, motion, and age. When starlight passes through a prism or diffraction grating, it spreads into a spectrum, a rainbow of colors from red to violet. But the spectrum is not continuous. It is crossed by dark lines at specific wavelengths, places where atoms in the star's atmosphere have absorbed light. Each element produces a unique pattern of absorption lines, a fingerprint that allows astronomers to identify what the star is made of without ever visiting it. Spectroscopy, the study of these spectral lines, revolutionized our understanding of stars. In the 19th century, astronomers discovered that stars contain the same elements found on Earth. hydrogen and helium and iron and calcium, and dozens of others. The universality of the elements was a profound realization. It meant that the same physical laws govern matter everywhere in the universe, that the atoms in a distant star are identical to the atoms in your hand. The universe is made of one substance, arranged in countless different forms. The temperature of a star determines its color and the shape of its spectrum. Hot stars emit most of their light at blue and ultraviolet wavelengths. Cool stars emit most of their light at red and infrared wavelengths. By measuring the spectrum of a star, astronomers can determine its surface temperature with great precision. This temperature, combined with the star's luminosity, allows astronomers to place the star on a diagram that reveals its evolutionary state and physical properties. The Hertzsprung-Russell diagram is one of the most important tools in stellar astronomy. It plots stars according to their luminosity and temperature, revealing patterns that correspond to different stages of stellar evolution. Most stars fall along a diagonal band called the main sequence, where they spend the majority of their lives fusing hydrogen into helium. Red giants and supergiants occupy a region above and to the right of the main sequence, luminous but cool. White dwarfs cluster in a region below and to the left, faint but hot. The diagram is a map of stellar life, showing where stars are born, how they change, and where they end up. The position of a star on the Hertzsprung-Russell diagram is determined primarily by its mass. Massive stars are hot and luminous, occupying the upper left of the main sequence. Low-mass stars are cool and faint, occupying the lower right. As a star ages and its internal structure changes, it moves across the diagram, tracing a path that depends on its initial mass and composition. By studying the distribution of stars on the diagram, astronomers can reconstruct the history of star formation in a cluster or galaxy and predict the futures of individual stars. The main sequence is not a single line, but a band with some width. Stars of the same mass can have slightly different luminosities and temperatures depending on their age and chemical composition. A star just arriving on the main sequence is called a zero-age main sequence star. As it burns hydrogen and accumulates helium ash in its core, it gradually becomes slightly more luminous and moves slightly upward on the diagram. This evolution is slow, taking millions or billions of years, but it is measurable in star clusters where many stars of the same age can be compared. The turn-off point of a star cluster is the location on the Hertzsprung-Russell diagram, where stars are just beginning to leave the main sequence. By measuring the turn-off point, astronomers can estimate the age of the cluster. In a young cluster, even massive luminous stars are still on the main sequence, and the turn-off point is high. In an old cluster, the massive stars have long since evolved and died, and the turn-off point is lower, corresponding to less massive, longer-lived stars. This technique has been used to date globular clusters at more than 12 billion years old, making them among the oldest objects in the galaxy. Stars do not emit light uniformly in all directions at all wavelengths. Some stars have spots, regions of the surface that are cooler or hotter than average. Others have magnetic activity that varies over time, producing changes in brightness and spectral features. Rapidly rotating stars can be flattened at the poles and bulging at the equator, distorting their shapes and affecting how their light varies as they spin. The surfaces of stars are dynamic places, subject to convection, magnetic fields, and other forces that create patterns and variations visible from light years away. Star spots are analogous to sunspots, regions where magnetic fields inhibit convection and lower the local temperature. On some stars, star spots can cover a significant fraction of the surface, causing noticeable variations in brightness as the star rotates and different hemispheres come into view. By tracking these brightness variations over time, astronomers can measure the rotation periods of distant stars and map the distribution of spots on their surfaces. Some stars rotate in just a few hours, while others take months to complete a single turn. Stellar rotation affects many aspects of stellar evolution. Rapidly rotating stars mix their interiors more efficiently, bringing fresh hydrogen down to the core and prolonging their main sequence lifetimes. Rotation also affects mass loss, with material being flung off the equator of rapidly spinning stars. In close binary systems, tidal interactions can synchronize the rotation of the stars with their orbital period, locking them in a gravitational embrace that affects their evolution in complex ways. The magnetic fields of stars are generated by dynamo processes in their interiors, where the combination of convection and rotation produces electric currents that create and sustain magnetic fields. The strength and geometry of a star's magnetic field depend on its rotation rate, its internal structure, and other factors that are still not fully understood. Some stars have relatively simple, dipolar magnetic fields like the Earth's. Others have complex, multipolar fields that vary rapidly over time. Magnetic activity is associated with stellar youth, with young stars typically being more active than older ones. Stellar flares are sudden releases of magnetic energy that can briefly increase a star's brightness by factors of hundreds or thousands. Flares occur when stressed magnetic field lines reconnect, converting magnetic energy into heat, light, and fast-moving particles. The sun produces flares regularly, though most are small enough that we barely notice them. Some stars, particularly young red dwarfs, produce flares vastly more powerful than anything the sun has ever generated, capable of doubling or tripling the star's brightness in a matter of minutes. Flares from red dwarf stars have implications for the habitability of planets orbiting those stars. Because red dwarfs are small and cool, their habitable zones are very close to the star, and planets there are exposed to intense flare radiation. A powerful flare could strip away a planet's atmosphere or sterilize its surface. Whether planets around red dwarfs can develop and maintain conditions suitable for life is still an open question, one that depends on the frequency and intensity of flares and the ability of atmospheres to regenerate after being damaged. The nearest star to our Sun, Proxima Centauri, is a red dwarf with a known planet in its habitable zone. Proxima b, as the planet is called, orbits so close to its star that its year is only 11 Earth days long. But Proxima Centauri is an active star, prone to flares that could make conditions on Proxima b quite harsh. Whether Proxima b has an atmosphere, whether that atmosphere could survive the flare bombardment, and whether any form of life could exist, there are questions that future observations may help answer. The search for planets around other stars has revealed a universe far richer and stranger than anyone anticipated. As of now, more than 5,000 exoplanets have been confirmed, and thousands more candidates await verification. These planets come in an astonishing variety: hot Jupiters that orbit closer to their stars than Mercury does to the Sun, super-Earths with masses between Earth and Neptune, mini-Neptunes shrouded in thick atmospheres, and potentially rocky worlds in the habitable zones of their stars. The first exoplanet around a Sun-like star was discovered in 1995, orbiting the star 51 Pegasi. The planet, 51 Pegasi b, was a surprise. It was a gas giant similar in mass to Jupiter, but it orbited its star in just 4 days, far closer than anyone had expected such a planet to exist. This hot Jupiter challenged existing theories of planet formation and opened a new era of exoplanet discovery. Since then, the pace of discovery has accelerated, driven by space telescopes like Kepler and TESS that can monitor thousands of stars simultaneously for the tiny dips in brightness caused by transiting planets. The transit method detects planets by measuring the slight dimming of a star as a planet passes in front of it. The amount of dimming depends on the size of the planet relative to the star. A Jupiter-sized planet transiting a Sun-like star causes a dip of about 1%. An Earth-sized planet causes a dip of only about 1/100%, a signal so small that it requires exquisitely precise measurements to detect. Despite these challenges, the Kepler Space Telescope discovered thousands of planets during its 9-year mission, revealing that planets are common throughout the galaxy. The radial velocity method detects planets by measuring the gravitational wobble they induce in their host stars. As a planet orbits, it tugs on the star, causing the star to move in a small circle or ellipse. This motion can be detected as a periodic shift in the wavelengths of the star's spectral lines, a Doppler shift that reveals the presence and mass of the planet. The radial velocity method was used to discover 51 Pegasi b and many other exoplanets, and it remains an important tool for characterizing planetary systems. Some exoplanets have been directly imaged, their light separated from the overwhelming glare of their host stars. Direct imaging is extremely challenging because stars are millions or billions of times brighter than the planets orbiting them. Special instruments called coronagraphs block the starlight, allowing the faint glow of planets to be seen. Direct imaging works best for young, massive planets that are still warm from their formation and emit significant infrared radiation. Several dozen exoplanets have been imaged this way, revealing worlds unlike anything in our solar system. The diversity of exoplanets is remarkable. Some orbit so close to their stars that their surfaces are molten rock, tidally locked with one face eternally baked by starlight and the other frozen in perpetual darkness. Others orbit at vast distances, taking centuries to complete a single orbit, their surfaces so cold that most gases would freeze solid. Some planets orbit binary stars, experiencing double sunrises and sunsets. Others have been ejected from their planetary systems entirely and wander through interstellar space, rogue planets drifting alone in the darkness. Water worlds may be common in the galaxy, planets covered entirely by oceans hundreds of kilometers deep. On such worlds, the pressure at the seafloor would be so immense that water would be compressed into exotic, high-pressure ice phases, even at temperatures far above freezing. What kinds of life, if any, could exist on such worlds is a matter of speculation. The oceans would be vast and deep, cut off from any rocky seafloor that might provide the chemical gradients thought to be important for the origin of life. Lava worlds exist at the opposite extreme, planets so hot that their surfaces are covered in molten rock. These worlds orbit extremely close to their stars, their surfaces baked to temperatures exceeding 1,000 degrees. Some lava worlds may have atmospheres of vaporized rock, with clouds of silicate droplets and rain made of liquid stone. The conditions are so extreme that they seem incompatible with any form of life we can imagine. Yet they offer laboratories for studying planetary physics under conditions we cannot reproduce on Earth. Some exoplanets orbit in the habitable zones of their stars, the region where temperatures might allow liquid water to exist on the surface. The habitable zone depends on the star's luminosity and the planet's atmosphere. A planet with a thick greenhouse atmosphere might be warm enough for liquid water, even if it orbits beyond the nominal habitable zone. A planet with no atmosphere might be frozen even in the middle of the zone. The presence of a planet in the habitable zone does not guarantee habitability, but it is a promising sign that conditions might be right for life. The TRAPPIST-1 system contains 7 Earth-sized planets orbiting a small red dwarf star about 40 light-years away. 3 of these planets are in the habitable zone, and all 7 are close enough together that they would be visible in each other's skies. If you stood on one of the TRAPPIST-1 planets, you might see neighboring worlds as large as the Moon or even larger, their surfaces and features visible to the naked eye. The system is a natural laboratory for studying planetary atmospheres and the potential for life around red dwarf stars. The James Webb Space Telescope is beginning to characterize the atmospheres of exoplanets, searching for the chemical signatures of habitability and life. By measuring the light that passes through a planet's atmosphere as it transits its star, astronomers can detect the absorption features of specific molecules. Water vapor, carbon dioxide, methane, and other gases leave distinctive fingerprints in the spectrum. The presence of certain combinations of gases, particularly oxygen and methane together, might indicate biological activity, though other explanations would need to be ruled out. The search for biosignatures is one of the most exciting frontiers in astronomy. If life exists on other worlds, it may alter the chemistry of planetary atmospheres in detectable ways. On Earth, oxygen is produced almost entirely by photosynthesis, and its presence in our atmosphere is a sign of life. Methane is produced by microbes and would quickly disappear from the atmosphere if it were not constantly replenished. A planet with both oxygen and methane in its atmosphere would be difficult to explain without invoking some form of biology. But detecting biosignatures is not the same as proving the existence of life. Many abiotic processes can produce gases that mimic the signatures of life. Oxygen can be produced by the photolysis of water vapor, methane can be released by volcanic activity, and complex chemistry can occur in atmospheres without any biology at all. Distinguishing true biosignatures from false positives will require careful analysis and a deep understanding of planetary chemistry. Even a strong detection would likely be debated for years before any consensus emerged. The distances to even the nearest stars are so vast that traveling to them with current technology would take tens of thousands of years. Proxima Centauri, the closest star, is about 4 light-years away. A spacecraft traveling at the speed of the Voyager probes, about 17 kilometers per second, would take more than 70,000 years to reach it. Faster technologies, such as nuclear propulsion or light sails, might reduce the travel time to decades or centuries, but even these remain largely theoretical. For the foreseeable future, we will study exoplanets from afar, limited to the light and signals they send us. Light itself is our only messenger from the stars. Photons that left a distant star years or centuries or millennia ago arrive at our telescopes, carrying information about their source. We cannot touch the stars, cannot send probes to study them directly, cannot know them except through the light they emit, and yet that light is enough to reveal their temperatures, compositions, motions, and ages. It is enough to detect planets orbiting them, to measure the chemicals in those planets' atmospheres, to search for signs of life across the cosmic abyss. Light is the thread that connects us to the universe. The finite speed of light means that we are always looking into the past. The light from Proxima Centauri that reaches us tonight left that star 4 years ago. The light from the Andromeda Galaxy left 2.5 million years ago, before humans existed. The light from distant quasars left billions of years ago, when the universe was young and galaxies were still forming. Every observation is an act of cosmic archaeology, revealing not what is, but what was. The universe we see is a mosaic of different moments in time, assembled from light that has traveled different distances to reach us. This delay has practical implications for our understanding of stellar evolution. When we observe a star cluster, we see all the stars as they were at the same moment in the past, their light having traveled the same distance to reach us. But when we observe individual stars scattered across the sky, we see them at different moments in their lives, their light having traveled different distances. A nearby red giant might be seen as it was a few hundred years ago, while a distant blue supergiant might be seen as it was thousands of years ago. We assemble our understanding of stellar evolution from these scattered snapshots, piecing together the story of stellar life from stars at different distances and different ages. The study of stars is ultimately the study of physics under extreme conditions. The temperatures, pressures, and densities inside stars far exceed anything we can create on Earth. The nuclear reactions that power stars can only be studied directly in particle accelerators, and even then, the conditions are a pale imitation of stellar interiors. Yet our theoretical understanding has become remarkably complete. We can model the structure and evolution of stars with great accuracy, predicting how they will change over millions and billions of years. These models are tested against observations, and where they fail, we learn something new about the physics of matter and energy. Stellar astrophysics has benefited enormously from advances in computational power. Modern stellar models simulate the complex interplay of nuclear reactions, energy transport, convection, rotation, magnetic fields, and mass loss. They track the changing composition of a star as fusion converts one element into another. They follow the contraction and expansion of stellar layers as the star evolves. Running these simulations requires powerful computers, but the results are remarkably successful at reproducing what we observe in real stars. Asteroseismology is a technique that uses the natural oscillations of stars to probe their interiors, just as seismologists use earthquakes to study the Earth's interior. Asteroseismologists use stellar oscillations to measure the density, temperature, and composition profiles inside stars. These oscillations appear as tiny periodic variations in a star's brightness, caused by sound waves trapped inside the star. The patterns of oscillation depend on the star's internal structure, allowing astronomers to peer beneath the surface without ever going there. The Sun is the most intensively studied star, and helioseismology has revealed exquisite details about its interior. We know the depth of the convection zone, the rotation rate at different depths, and the temperature profile from the surface to the core. These measurements have tested and refined our models of stellar structure, revealing both the successes and the limitations of our understanding. The Sun serves as a benchmark, a nearby star that we can study in extraordinary detail and use to calibrate our understanding of all other stars. Solar neutrinos provided one of the most important tests of our understanding of stellar interiors. The nuclear reactions in the Sun's core produce neutrinos, ghostly particles that pass through matter almost without interacting. Detecting these neutrinos directly confirms that nuclear fusion is occurring in the Sun's core. In the 1960s, the first solar neutrino experiments detected fewer neutrinos than predicted, a discrepancy that puzzled physicists for decades. The solution turned out to involve not stellar physics, but particle physics. The discovery that neutrinos can change from one type to another as they travel, reducing the number detected. This neutrino oscillation was later confirmed and earned a Nobel Prize. The story of solar neutrinos illustrates how the study of stars can reveal fundamental physics. The Sun became a laboratory for testing ideas about particles and forces that had nothing to do with astronomy. Similar connections continue to be made today. Observations of neutron stars test our understanding of matter at nuclear densities. Observations of black holes test the predictions of general relativity. The universe is a laboratory, and stars are some of its most important experiments. Stellar archaeology uses the chemical compositions of old stars to reconstruct the history of the galaxy. The oldest stars preserve a record of the chemical enrichment of the early universe, their atmospheres containing the elements produced by the first generations of supernova. By measuring the abundances of different elements in these ancient stars, astronomers can infer the masses and explosion mechanisms of the stars that came before. Each old star is a time capsule carrying information about conditions billions of years ago. Some old stars show unusual abundance patterns that hint at exotic origins. Stars with extremely low iron, but relatively high carbon, may have formed from gas enriched by a single supernova with unusual properties. Stars with enhanced heavy elements may have formed from gas enriched by a neutron star merger. By cataloging these unusual stars and comparing their abundances to theoretical predictions, astronomers are piecing together the history of nucleosynthesis in the galaxy, one ancient star at a time. The chemical evolution of galaxies is driven by the life cycles of stars. Young galaxies are dominated by hydrogen and helium, with few heavy elements. As generations of stars live and die, they enrich the interstellar medium with heavier elements, and subsequent generations of stars form from this enriched material. The metallicity of a galaxy increases over time, and the pattern of enrichment depends on the history of star formation and the types of stars that have lived and died. By measuring metallicities across different galaxies and at different cosmic epochs, astronomers trace the buildup of heavy elements over the history of the universe. Galaxies at high redshift, seen as they were billions of years ago, show systematically lower metallicities than nearby galaxies. They are younger, and fewer generations of stars have had time to enrich their gas. The most distant galaxies we can observe existed when the universe was less than 1 billion years old, and they show the earliest stages of chemical enrichment, just a few generations removed from the primordial hydrogen and helium of the Big Bang. Observing these distant galaxies is like reading the early chapters of a book, seeing the universe when it was still young and stars were just beginning to forge the elements that would eventually become planets and life. The concept of stellar generations is a useful way to organize our thinking about cosmic chemical evolution. Population 3 stars, the first generation, formed from pristine gas and contained no heavy elements. Population 2 stars, the second generation, formed from gas enriched by population 3 supernovae and contained small amounts of heavy elements. Population 1 stars, including our Sun, are the most recent generation, formed from gas that has been enriched by many generations of stellar death. The boundaries between these populations are not sharp, and real stars show a continuous range of metallicities, but the concept captures the essential idea of progressive enrichment over cosmic time. The Sun is a population 1 star, relatively rich in heavy elements compared to older stars. About 2% of the Sun's mass consists of elements heavier than hydrogen and helium, including oxygen, carbon, iron, and many others. This heavy element content made possible the formation of rocky planets like Earth, which are composed almost entirely of heavy elements. Without the enrichment provided by earlier generations of stars, there would be no silicon for rocks, no iron for cores, no carbon for life. The existence of Earth and everything on it depends on the deaths of stars that came before. The formation of our solar system was a local example of the same processes that operate throughout the galaxy. About 4.6 billion years ago, a cloud of gas and dust in the Milky Way began to collapse under its own gravity. The center of the cloud became the Sun, while the surrounding disk of material gave rise to the planets, moons, asteroids, and comets. The cloud was enriched with heavy elements from earlier supernovae, possibly triggered by a nearby supernova that also provided the initial push for the collapse. The solar system is a child of stellar death, born from the ashes of stars that lived and died long before the Sun existed. The heavy elements in the solar system are distributed unevenly. The inner planets are rocky, composed mostly of iron, silicon, oxygen, and magnesium. The outer planets are gas giants, composed mostly of hydrogen and helium, with cores of heavier elements. The asteroids and comets preserve primitive material from the early solar system, relatively unaltered since the time of formation. By studying these different bodies, we reconstruct the conditions in the early solar system and trace the origins of the elements that make up our world. Meteorites provide a direct window into the early solar system. These fragments of asteroids and other small bodies fall to Earth and can be collected and analyzed in laboratories. Some meteorites contain tiny grains that predate the solar system itself. Pre-solar grains formed in the atmospheres of ancient stars and preserved through the formation and evolution of the solar system. These grains carry isotopic signatures that reveal the types of stars that produced them: red giants, supernovae, and other stellar sources. Holding a pre-solar grain is holding a piece of a star that died before the Sun was born. The study of pre-solar grains has revealed the diversity of stellar sources that contributed to the solar system's raw materials. Some grains formed in the cool winds of asymptotic giant branch stars. Others formed in the ejecta of supernovae. Still others show isotopic signatures that are difficult to explain with any known stellar process, hinting at sources we have not yet identified. The solar system is a melting pot. assembled from material contributed by many different stars over millions of years before the Sun itself began to form. Stars will continue to form in the Milky Way for billions of years to come, but the rate of star formation is gradually declining. The raw material for new stars, the cold gas in molecular clouds, is being consumed faster than it is replenished. Some gas is converted into stars. Some is heated by stellar feedback and driven out of the galaxy. Some falls onto the supermassive black hole at the galactic center. Over cosmic time, the supply of gas will dwindle, and star formation will slow to a trickle. In the far future, the Milky Way will become a red and quiet place. The massive blue stars will be long gone, having lived their brief lives and exploded as supernovae billions of years earlier. The sun-like yellow stars will have evolved into white dwarfs. Only the red dwarfs will remain, slowly burning their hydrogen fuel, their dim light the only illumination in a darkened galaxy. These red dwarfs will shine for trillions of years, far longer than the current age of the universe, patient sentinels in an aging cosmos. Eventually, even the red dwarfs will exhaust their fuel and fade into black dwarfs, cold and dark. The white dwarfs will cool to the same fate. The neutron stars will spin down and grow cold. The black holes will slowly evaporate through Hawking radiation, a quantum process that causes them to lose mass over unimaginably long timescales. In the end, the universe will contain only cold remnants and diffuse radiation, the faint echo of a time when stars burned bright. But that end is so far in the future that it defies comprehension. Trillions of years will pass before the last red dwarf fades. Trillions more before the black holes evaporate. The timescales of stellar death extend so far beyond human experience that they become abstract, numbers without intuitive meaning. For now, the stars continue to shine, and new stars continue to form, and the universe remains bright and dynamic. We live in an early chapter of a very long story. The death of a star is not always a solitary event. In binary systems, the fate of one star can profoundly influence the fate of its companion. When a massive star in a close binary explodes as a supernova, the explosion can kick the remaining neutron star or black hole out of the system entirely, sending it hurtling through the galaxy at hundreds of kilometers per second. Or the binary can remain bound, now containing a compact remnant orbiting a normal star, setting the stage for dramatic interactions later in the system's evolution. X-ray binaries are systems where a neutron star or black hole is actively pulling material from a companion star. The material spirals inward, forming a hot accretion disk that glows brightly in X-rays. These systems are among the most luminous X-ray sources in the galaxy, visible across vast distances. The flickering of their X-ray emission reveals the violent processes occurring near the surface of the neutron star, or just outside the event horizon of the black hole. X-ray binaries are laboratories for studying matter under extreme conditions, places where gravity and radiation interact in ways we cannot replicate on Earth. Some X-ray binaries are transient, spending most of their time in a quiet state before suddenly flaring to life as material accumulates and then cascades onto the compact object. These outbursts can increase the X-ray brightness by factors of thousands, making the system temporarily one of the brightest sources in the X-ray sky. The outbursts typically last for weeks or months before the system fades back into quiescence, waiting for the next episode of accretion. Millisecond pulsars are neutron stars that have been spun up to extraordinary rotation rates by accreting material from a companion star. The transfer of angular momentum from the infalling material accelerates the neutron star's rotation, eventually producing pulsars that spin hundreds of times per second. The fastest known millisecond pulsar rotates 716 times per second, its surface moving at a significant fraction of the speed of light. These rapidly spinning neutron stars are incredibly stable rotators, their pulse arrival times predictable to within billionths of a second over years of observation. The precision of millisecond pulsars makes them useful for detecting gravitational waves through a different method than ground-based detectors. By monitoring an array of millisecond pulsars scattered across the sky, astronomers can search for the subtle stretching and squeezing of space caused by passing gravitational waves. These pulsar timing arrays are sensitive to gravitational waves with periods of years or decades, far longer than the waves detected by LIGO and Virgo. In 2023, pulsar timing arrays reported evidence for a background of gravitational waves permeating the universe, possibly produced by the mergers of supermassive black holes in distant galaxies. Double neutron star systems are rare, but scientifically valuable. These systems contain two neutron stars orbiting each other, spiraling slowly inward as they lose energy to gravitational wave emission. The first double neutron star system was discovered in 1974 by Russell Hulse and Joseph Taylor, who observed that the orbital period was decreasing at exactly the rate predicted by general relativity for gravitational wave emission. This indirect detection of gravitational waves earned Hulse and Taylor the Nobel Prize in Physics and provided decades of precision tests of Einstein's theory. Eventually, double neutron star systems will merge. The final moments of inspiral are violent and spectacular, the two neutron stars touching and combining in a fraction of a second. The merger produces a burst of gravitational waves, a short gamma-ray burst, and a kilonova, a glowing cloud of heavy elements forged in the extreme conditions of the collision. The 2017 detection of a neutron star merger was a landmark event, the first time such an event was observed across multiple forms of radiation and gravitational waves simultaneously. The heavy elements produced in neutron star mergers include many that are rare on Earth, but essential for technology. Gold, platinum, and other precious metals are created in the rapid neutron capture process that occurs during and after the merger. The amounts are staggering. A single merger can produce several Earth masses of gold, scattered across space at high velocity. These elements mix with the interstellar medium and eventually become incorporated into new stars and planets. The gold in your jewelry may have been forged in a neutron star merger billions of years ago, traveling across the galaxy before becoming part of the Earth. Gamma-ray bursts are among the most energetic events in the universe. Long gamma-ray bursts, lasting more than a few seconds, are associated with the deaths of massive stars, their cores collapsing into black holes that launch relativistic jets through the stellar envelope. Short gamma-ray bursts, lasting less than about 2 seconds, are associated with neutron star mergers. Both types release enormous amounts of energy in gamma rays, briefly outshining everything else in the observable universe. If a gamma ray burst occurred nearby and its jet were pointed at Earth, the radiation could have devastating effects on our atmosphere and biosphere. Fortunately, Gamma ray bursts are rare, and the odds of one affecting Earth are extremely small. The nearest known gamma ray burst progenitors are thousands of light years away, and the jets are narrowly focused, reducing the chance that Earth would be in the beam. Over the history of the planet, it is possible that one or more gamma ray bursts have affected Earth, potentially contributing to mass extinction events. But such events are speculative, and the geological evidence is ambiguous. Supernovae within a few tens of light years of Earth could also have significant effects, showering the planet with cosmic rays and potentially damaging the ozone layer. There is some evidence that supernovae have occurred at such distances in the past few million years, based on the detection of unusual isotopes in deep-sea sediments and on the Moon. These isotopes, produced in supernova explosions and carried to Earth by interstellar dust, provide a record of nearby stellar deaths. The effects on life, if any, are difficult to assess, but the proximity of such events is a reminder that the Earth is not isolated from the wider universe. The deaths of stars create some of the most visually stunning objects in the sky. Supernova remnants glow with the light of shocked gas, their filaments and shells painting the darkness with colors that reveal their temperatures and compositions. Planetary nebulae display intricate patterns shaped by stellar winds, magnetic fields, and the ejection of material from dying stars. These objects are ephemeral on cosmic timescales, lasting only tens of thousands of years before fading and dispersing. But they offer glimpses of stellar death that are both beautiful and informative. The Veil Nebula in the constellation Cygnus is the remnant of a supernova that exploded perhaps 20,000 years ago. The expanding shell of gas spans several degrees of sky and glows in delicate filaments of red, blue, and green. The colors correspond to different elements: hydrogen, oxygen, and sulfur, each emitting light at characteristic wavelengths as the gas is heated by the passage of the shock wave. The Veil Nebula is close enough and large enough that it can be observed in detail, revealing the complex structure of a supernova remnant as it interacts with the surrounding interstellar medium. The Crab Nebula mentioned earlier is the remnant of a supernova observed in the year 1054. Chinese astronomers recorded the appearance of a guest star so bright that it was visible in daylight for several weeks. The remnant we see today is an expanding cloud of gas and dust, powered by the rapidly spinning pulsar at its center. The Crab pulsar rotates about 30 times per second, emitting beams of radiation that sweep across Earth like a cosmic lighthouse. The energy released by the pulsar keeps the nebula glowing, a testament to the continuing influence of a star that died nearly 1,000 years ago. The Tycho and Kepler supernova remnants are named for the astronomers who observed the original explosions in 1572 and 1604, respectively. Both were bright enough to be seen with the naked eye, and both left behind expanding shells of gas that are still visible today. These historical supernovae occurred before the invention of the telescope, so the observations were made with the unaided eye. But the records left by Tycho Brahe and Johannes Kepler provide valuable information about the brightness and duration of the events. No supernovas has been observed in our galaxy since 1604, though several have been detected in nearby galaxies. The most recent supernova visible to the naked eye was SN 1987A, which occurred in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way about 168,000 light-years away. The explosion was first noticed on February 24, 1987, when observers in the southern hemisphere saw a new star where none had been visible before, SN 1987. A was the first supernova close enough for detailed study with modern instruments, and it provided a wealth of information about the physics of stellar explosions. The detection of neutrinos from the event confirmed theoretical predictions about core collapse and marked the beginning of neutrino astronomy. The star that exploded as SN 1987A was a blue supergiant, not the red supergiant that theory predicted. This surprise led to revisions in our understanding of supernova progenitors and the final stages of massive stellar evolution. The remnant of SN 1987A is still being monitored today. It's expanding debris interacting with material shed by the star before the explosion. A ring of glowing gas surrounds the explosion site, gradually brightening as the shock wave crashes into it. Somewhere at the center, there may be a neutron star, though it has not yet been definitively detected. Cassiopeia A is one of the youngest supernova remnants in our galaxy, the result of an explosion that occurred around the year 1680. Strangely, no historical records of the supernova have been found, suggesting that it may have been obscured by interstellar dust or simply not noticed. Today, Cassiopeia A is one of the brightest radio sources in the sky and a favorite target for X-ray and infrared telescopes. The remnant shows a complex structure of knots and filaments, the remains of the star's outer layers expanding at thousands of kilometers per second. The expanding debris from supernovae eventually merges with the interstellar medium, dispersing the heavy elements created in the explosion and contributing to the enrichment of the galaxy. This process takes thousands of years, with the shockwave gradually slowing and the gas cooling and mixing with its surroundings. The material ejected by one supernova may eventually become part of a molecular cloud that collapses to form new stars, continuing the cycle of stellar birth and death that has been operating since the first stars formed. The rate of supernovae in the Milky Way is estimated at about 1 to 3 per century, though many are hidden from view by interstellar dust. Supernovae in the bulge of the galaxy, where dust is densest, would be almost impossible to observe in visible light. Future supernova searches will rely on neutrino detectors, gravitational wave observatories, and infrared telescopes that can peer through the dust. When the next galactic supernova occurs, astronomers around the world will be alerted within seconds, ready to turn every available instrument toward the explosion. A nearby supernova would be a spectacular event for observers on Earth. A supernova at the distance of Betelgeuse, about 650 light-years away, would be as bright as the full moon for several weeks, easily visible in daylight and casting shadows at night. The sight would be unforgettable, a new star blazing in the sky, outshining everything except the sun and moon. Such an event would pose no danger to Earth, the distance being far too great for the radiation to cause harm. But it would be a reminder of the violent processes that shape the cosmos. Betelgeuse, the red supergiant that marks the shoulder of Orion, is often mentioned as a supernova candidate. The star is nearing the end of its life, its core fusing heavier and heavier elements as it progresses toward iron. When the iron core collapses, Betelgeuse will explode, leaving behind either a neutron star or a black hole. The timing is uncertain. It could happen tomorrow or in 100,000 years, but in cosmic terms, the explosion is imminent. Observers have noted variations in Betelgeuse's brightness over the years, including a dramatic dimming in late 2019 and early 2020 that sparked speculation about an impending supernova. The dimming turned out to be caused by a cloud of dust ejected by the star, not a sign of imminent collapse, but the episode highlighted the ongoing interest in this fascinating star. Eta Carinae is another massive star that may explode in the astronomically near future. The system contains two stars, the more massive of which is one of the most luminous and unstable stars known. The Great Eruption of the 1840s, when Eta Carinae briefly became the second brightest star in the sky, ejected several solar masses of material and created the homunculus nebula that surrounds the system today. The star is thought to be near the end of its life, though the exact timescale is uncertain. When Eta Carinae explodes, it may produce a particularly energetic supernova, possibly even a hypernova or a gamma-ray burst. Wolf-Rayet stars are another class of massive stars destined for violent ends. These stars have lost their outer hydrogen envelopes, exposing the products of nuclear fusion in their cores. They are extremely hot and luminous, with powerful stellar winds that carry away mass at prodigious rates. Wolf-Rayet stars are the immediate progenitors of some core collapse supernovae, their stripped cores collapsing when the fuel runs out. The supernovae produced by Wolf-Rayet stars may be particularly bright or energetic, their lack of a hydrogen envelope allowing the explosion to be seen more directly. The most massive stars may end their lives not in supernovae, but in direct collapse to black holes. If the core is massive enough, the collapse may proceed so rapidly that no explosion occurs, the entire star simply vanishing from view as it falls into the newly formed black hole. These failed supernovae would be difficult to detect, their only signature the sudden disappearance of a star that was there one moment and gone the next. A few candidate events have been identified, massive stars that faded from view without any accompanying explosion, but confirming these as direct collapses remains challenging. Pair instability supernovae, mentioned earlier, represent the most extreme stellar deaths. These occur in the most massive stars, with cores so hot that photons convert into electron-positron pairs, triggering a runaway collapse and explosion that completely destroys the star. No remnant is left behind. No neutron star or black hole, just an expanding cloud of debris enriched with the products of explosive nucleosynthesis. Pair instability supernovae have not been definitively observed, but some extremely luminous supernovae discovered in recent years may be examples of this process. Superluminous supernovae are a class of explosions that are 10 to 100 times brighter than typical supernova. Their energy source is debated. Some may be powered by the interaction of the supernova ejecta with dense material shed by the star before the explosion. Others may be powered by a rapidly spinning neutron star, a magnetar, at the center of the remnant, its rotational energy converted into radiation that keeps the supernova glowing. Still others may be pair instability supernova or other exotic phenomena. Superluminous supernovae are rare, but they can be seen across enormous distances, making them valuable probes of star formation in the early universe. The variety of stellar deaths reflects the diversity of stellar lives. Stars of different masses, compositions, and environments meet different ends, their deaths shaped by the same physical processes that govern their births and lives. The study of stellar death is inseparable from the study of stellar life, each informing the other in a continuous cycle of understanding. Every supernova, every planetary nebula, every white dwarf and neutron star is a piece of evidence, a clue to the physics of matter and energy under extreme conditions. The universe is constantly changing, stars being born and dying at every moment. In the time it takes to read this sentence, several stars have probably formed somewhere in the observable universe, and several others have died. The numbers are staggering. Billions of stars living and dying over the history of the cosmos, each one contributing to the chemical enrichment and structural evolution of its galaxy. We are witnesses to a moment in this ongoing story, privileged to observe the universe at a time when stars are abundant and galaxies are bright. The night sky that we see from Earth is a snapshot, a frozen moment in a dynamic process that unfolds over timescales far longer than human lives. The constellations that our ancestors named will eventually dissolve, their stars drifting apart as they orbit the galaxy. New constellations will form, patterns that no human has ever seen, the shifting arrangements of stars over millions of years. The sky is not fixed, but flowing, a river of stars that we perceive as stillness only because our lives are so brief. And yet, there is a continuity that transcends the changes. The same physical laws that govern stars today govern them billions of years ago and will govern them billions of years from now. The processes of nuclear fusion, gravitational collapse, and radiative transfer are universal, operating in the same way wherever and whenever they occur. The story of stellar evolution is the same story everywhere in the universe, with local variations, but a common plot. Stars are born, they shine, and they die, and from their deaths come the seeds of new stars and new worlds. The elements created in stars do not vanish when the stars die. They persist, drifting through space, gathering into new clouds, forming new stars and planets. The iron in your blood has been through at least one star, possibly several. The oxygen you breathe has traveled across the galaxy, part of a journey that began billions of years ago in the core of a massive star. You are a temporary arrangement of atoms that have been part of many other arrangements before you, and will be part of many others after you are gone. The atoms are ancient, only the pattern is new. This perspective can bring a sense of connection to the cosmos. We are not separate from the universe, but part of it, made of the same stuff as stars and galaxies, participating in these same processes that have been operating since the beginning of time. The boundary between self and cosmos is an illusion, a convenient fiction that helps us navigate our daily lives, but dissolves under scrutiny. We are stardust, as the poets and scientists both remind us, and the stars are our kin. The night sky invites contemplation. It has done so for as long as humans have existed, and probably for as long as any beings anywhere have looked upward and wondered. The questions we ask today about the nature of stars, the origins of elements, the fate of the universe, are the same questions our ancestors asked, though we have better tools and more answers. And yet, the mystery remains. For every question we answer, new questions arise, leading us deeper into the complexity and beauty of the cosmos. As you listen to these words, stars are being born in distant nebulae, their first light just beginning to shine. Other stars are dying, their cores collapsing or their outer layers drifting into space. The universe is alive with change, a vast and intricate dance of matter and energy that has been going on for billions of years. You are part of this dance, a brief flicker of consciousness in a cosmos that is mostly dark and mostly empty, but punctuated by points of light and warmth that we call stars. Perhaps you are still awake, following the journey of stellar birth and death through to its end. Or perhaps you have already drifted off, carried into sleep by the gentle rhythm of these words. Either way, the stars continue their ancient work, burning hydrogen into helium, forging heavy elements in their cores, scattering those elements across space when they die. The cycle goes on, indifferent of whether anyone is watching, a process so slow and so vast that our entire civilization is less than a blink in its duration. The light from distant stars reaches your eyes tonight. Photons that have traveled for years or centuries or millennia to arrive at this moment. Each photon carries a tiny piece of information about its source, the temperature, composition, and motion of a star you will never visit. The universe is telling you its story through these messengers of light, whispering secrets that patient observation can decode. All you need to do is look up and wonder. And now, as this journey draws to a close, you can let your thoughts drift like starlight across the void. We have traveled from the cold clouds where stars are born to the brilliant fires of main sequence life, from the swelling of red giants to the quiet cooling of white dwarfs, from the violence of supernovas to the strange stillness of neutron stars and black holes. We have traced the elements from stellar cores to interstellar space to new generations of stars and planets. We have glimpsed the far future, when the last red dwarfs will fade and the universe will grow cold. But that future is unimaginably distant, for now the stars continue to shine and new stars continue to form, and the universe remains a place of light and warmth and wonder. You are here in this moment, breathing air made of atoms forged in ancient stars, your body a temporary home for elements that have journeyed across billions of years to be part of you. You are the universe experiencing itself, a collection of stardust that has learned to wonder about the stars. If you are still awake, you can go ahead and watch the next video now. The stars will be waiting, as they always are, silent and patient in the darkness. If your eyes are heavy and sleep is near, let yourself drift into rest, carried by the quiet hum of the cosmos, the distant light of 100 billion suns, the ancient rhythm of stellar birth and death that has been unfolding since the universe began and will continue long after we are gone. Sleep well and dream softly. The stars will keep their vigil through the night, burning steadily in the void, and when you wake, they will still be there. A canopy of light spread across the darkness, reminding you that you are part of something vast and beautiful and very, very old. Good night.